Hi class, welcome to chapter 12, water and the major minerals. So today we're going to talk about sodium, potassium, calcium, chloride, phosphorus, magnesium, and quite a few more, as well as the role that water plays in the body. So, how much of the body is made up of water? Hopefully you remember that approximately 60% or more or less, depending on age and gender of our body, is made up of water. So most of our body is made up of water. Therefore, it is so important to health. Functions of water. Helps carry nutrients and waste products. So nutrients to the tissues, waste away from the body in the form of urine. Maintains structures of proteins and glycogen. Remember, we do require water in order to store glycogen. Is important for metabolic reactions. Is a solvent, which is kind of like a fluid component for different molecules. Lubricates and cushions our joints and our eyes. So water is important to form the different fluids and liquids that cushion, the space between our vertebrae and our mucous membranes. Helps with body temperature regulation. So by sweating, we can regulate our temperature. And maintains our blood volume. Our blood is primarily made of water. Without water, we would not have adequate blood volume and couldn't carry oxygen to all the cells. So overall, water is pretty important. Fluids in the body. So water is the primary fluid in the body, and we can categorize fluids based on where they're located. So we have intracellular fluids, and intracellular fluids are within the cell. And then we have extracellular fluids. And extracellular fluids are outside of the cell, and they can either be within the blood vessels, in which case they're referred to as being intravascular, or they can be intercellular or interstitial, meaning between the cells, but not within the cells. So we have intracellular and extracellular fluid, and with regards to extracellular fluid, there are a couple different types. Water intake. So obviously you guys have felt thirst before, and when you get thirsty, your body signals you to drink more water. The thirst response is triggered by the hypothalamus, and when we're not drinking enough water, one of the things that happens is our blood volume can drop, and the nutrients or possibly even contaminants or electrolytes within our blood can become very concentrated. And in order to dilute these to appropriate levels, we need more water. Our mucous membranes can also dry out. So you might have kind of like a cotton mouth, you might feel like you have dry eyes, etc. And what will happen is our hypothalamus will tell us to start drinking. We'll drink water, we'll replace water, and then our mouth will be lubricated, we'll be able to have saliva, and our blood pressure will be regulated again. We also have receptors in the stomach that signal thirst, and we have receptors in the heart that monitor blood volume to signal both thirst as well as us to stop drinking. Why would we need to stop drinking? So you can actually overdose on water. Yes, that is true. You can die from drinking too much water. And you would have to drink quite a lot of water to have this sort of a consequence, but somewhere between maybe 10 plus gallons or 10 to 20 liters of water would dilute your electrolytes so substantially that your body wouldn't be able to recover, and that could change the pH, destabilize proteins, enzymes wouldn't function, etc. So it is possible to overconsume water, and because of that, our body needs to have these different checks and balances to prevent that. Signs of dehydration. So thirst. However, thirst is actually kind of a late sign of dehydration. So if you are feeling thirsty, that means you're already dehydrated. And so you've already lost about 1 to 2% of your total body volume in fluid, which could represent like 60% of your body. So maybe you've lost 0.6% or something equivalent of that, and that could relate to a few pounds in water loss. So when you feel thirsty, it's actually a late response to being dehydrated and not having enough body fluid. The more severely you're dehydrated, the more body volume you will have lost, and this will cause you to have increasingly severe symptoms and could actually lead to death. So we don't have a big range for how much of our fluid we can lose. Where can we get fluid? We have many different sources of fluid. There are some obvious ones and there are some less obvious ones. So a obvious one would be water itself. Drinking water is a way for us to get water or fluids. Other beverages do contain, generally speaking, 90 to 99% water. So when we drink milk, when we drink juice, when we drink tea, even when we drink coffee, all of those things are primarily made of water. Foods that we consume have a lot of water, and we'll see some ranges for what percent of each food is composed of water, but some foods have like 98% water, such as iceberg lettuce or watermelon, if you don't count the seeds or the rind. And then the last source of water to our bodies is actually our own body's metabolic reactions. And so anytime our body is performing a condensation reaction where it's combining two molecules, water is produced as a byproduct. So the example in this diagram is the combining of two amino acids to form a protein. So when we're doing these building reactions, we can have water being created as a byproduct, and this can contribute 200 to 300 milliliters per day. This is a chart showing what percent of water is in different food sources. So strawberries, watermelon, lettuce, like I mentioned, cabbage, celery, spinach, broccoli. Many of those vegetables and fruits are very high in water, 90 to 90%. Even things like ice cream are very high in water. Chicken breast, who would have thought that was super watery? Pasta that's been cooked, not raw, pizza, pepperoni, etc. You see, as you get to the bottom of this chart and the water percentages decline, the foods tend to have higher fat content and be generally just kind of dried foods such as taco shells or pretzels. But foods with high fats are going to have less water because water and fat are opposites to one another. So things like oils will have zero water. How do we get rid of water? So we've discussed how we can intake water and even produce it with our own body. The next job is to get rid of it. Otherwise, we would swell up like a balloon. And so the most obvious way we get rid of water is through our urinary tract. And the kidneys actually filter fluids in our body and deposit wastes into the fluid, which then travels down something called the ureter, which is pretty much a tube going to the bladder where it's stored until you're ready to go pee. The very, very minimum amount of fluid that the kidneys have to excrete a day in order to get rid of wastes is 500 milliliters per day. And that's called the obligatory water excretion level. So if you're not peeing at least 500 mils a day, your kidneys are going to have increasing difficulty to get rid of the waste products that have built up. The lungs are also a way for us to get rid of water, and you might not necessarily notice this, especially if the temperature is mild, but on a cold day, you can usually see your breath, or if you put, say, your glasses to your mouth and then breathe, you can usually see it get fogged up. That's water vapor. Sweat, many of you are probably familiar with this. And Feces is another way to get rid of water because feces is not dry. It is usually moist and hopefully not overly moist. It's possible to have excessive fluid losses through the feces in the case of diarrhea. So average total daily loss is 2.5 liters, and this will help us get rid of waste and regulate how much we have consumed or intaked during the day. So water balance is very important. Otherwise, we would either swell up like a balloon or our cells would shrink, and that would also be very dangerous. You can see on the left-hand side of this chart, water sources, so beverages, foods, metabolism. Obviously, these are going to vary from person to person. It's very possible for somebody to consume more or less food and beverage than this. And then water losses will also vary from person to person and depending on the situation. But these are an average, and what you can see is the average water intake is equal to the average water loss, maintaining fluid balance in our body. Water recommendations. So how much should we consume? There are different recommendations depending on age as well as activity level. For generally speaking, for adults, you should have 1 to 1.5 milliliters of water per calorie expended. So for example, if I have 2,000 calories that I'm using per day, I would need 2,000 milliliters of water. If I'm multiplying that by 1.5, I would need 3,000 milliliters of water. If you're an athlete or an infant, your water needs start at 1.5. Obviously, they could be higher for certain athletes depending on how strenuous the activity is and the weather and humidity outside. But athletes and infants generally need significant more fluid than adults or people who aren't in a growth state. And so, easy estimation, you can do a half cup per 100 calories expended. So if you are burning 2,000 calories, you could divide that by 100. You would get 20 half cups, which is the same as 10 full cups of water. But really, you should just drink until you're feeling satisfied. You can look at your urine color. Any dark urine color, dark orange, brown, represents that you are possibly dehydrated. Your urine should not have color. It should be clear or maybe faint yellow. And you can assess your mucous membranes, your eyes, your mouth, your saliva, your nose, etc. What about caffeinated beverages? So although caffeinated beverages can make you urinate more, which is a way to lose fluid, they are considered by the DRI committee as contributing positively to our fluid intake. So even things like coffee and tea, although they may increase some of our excretion of water, do still contribute. The kidneys are our main organ that regulates our fluid balance, and the kidneys are made up of thousands and thousands of tiny units called the nephron, which is tiny vascular units that include the glomerulus, capillaries, renal tubule, and then eventually feed to the ureters. And within the kidneys are able to determine how much fluid our body needs, as well as get rid of wastes and regulate electrolyte balance, so things like sodium and potassium. What will happen is blood will flow into the glomerulus, which is this kind of round portion of the kidney, and within the glomerulus, you'll have some absorption of some of the dissolved substances into the tubule. Those substances that head into the tubule, most of them will be excreted in the urine, but some of them can be reabsorbed, meaning they'll travel back to the blood vessels and go back to the body if we determine that we need them. What's left in the tubule will pass to the bladder and be excreted via urination. And this whole mechanism is mediated by multiple different hormones. They include renin, angiotensin, ADH or antidiuretic hormone, which is now called vasopressin, and aldosterone. And so in these ways, the kidneys are very kind of precise organs that can adjust the volume and concentration of the urine based on changes in fluid intake with the body and electrolytes, as well as waste buildup. So this is a cascade pathway that is representing how exactly these different hormones monitor changes in fluid within the body. So at the top, you have a situation of low blood volume. And when you have low blood volume, you're going to have low blood pressure. So maybe you've been in an accident and unfortunately you've been bleeding a lot and it's led to low blood volume. Well, what's going to happen is that low blood volume is going to trigger something called renin, which is a hormone. And renin is going to begin this cascade of events that's going to help increase your blood pressure. Because if your blood pressure gets too low, such as in the case of a bad injury, you're actually not able to pump that blood around the body and deliver nutrients and oxygen to all the organs, and some serious consequences can arise. So in order to prevent that, renin will trigger this cascade and it will cause angiotensin to be converted to angiotensin 1. This will be converted to angiotensin 2 by an enzyme, and angiotensin 2 has multiple functions. It can directly constrict the blood vessels, which means making the blood vessels more narrow, which if you had less total blood volume and you made your blood vessels more narrow, it would help increase the blood pressure. And angiotensin can also act on two hormones, one called antidiuretic hormone, or now called vasopressin, and one called aldosterone. Antidiuretic hormone is a hormone produced by the pituitary gland in response to dehydration or high sodium content in the blood, which will also indicate not enough fluid in the blood. And it will cause the kidneys to reabsorb more water and excrete less water. So that means less water will go to the bladder and more water will go back into the capillaries, which will go to the body. It also has an antidiuretic effect, so less water will be lost, and because of this, it helps to increase blood pressure. Aldosterone is a second hormone that will cause sodium retention, and water does follow sodium. It will also cause potassium excretion, and this can also help increase blood pressure. So this is a cascade of events that will happen during low blood pressure. This is a summary slide discussing those four hormones and how each of them acts to monitor and control blood pressure. And so it's important to know that antidiuretic hormone, renin, angiotensin, and aldosterone all play a role. Fluid and electrolyte balance. So electrolytes are charged particles, and when they dissolve in water, they can separate into ions. Ions may have positive or negative charges, and water can actually bind to ions. So, for example, sodium chloride, which is our basic table salt, when you drop that in water, it actually separates into sodium component and a chloride component. And each of those can bind with water in what's called an electrolyte solution. This is important because water will follow electrolytes, and the path of water to follow electrolytes can influence how much water is found inside and out of the cells. Cations and anions. So depending on the charge of each electrolyte, they may be referred to as a cation and an anion. And cations have positive charges, and the amount of cations must balance the amount of anions, which have negative charges. So sodium, potassium, calcium, and magnesium all have positive charges, and chloride, bicarbonate, phosphate, sulfate, and different organic acids all have negative charges. And so within the cell as well as outside the cell, we like all the positive charges to be equivalent to the negative charges. So here we have our cations, which have positive charges, and inside the cell we have potassium and we have magnesium. And potassium is going to have a positive charge. Each of these green circles are going to have positive charges. And potassium is the main intracellular cation. Phosphorus is going to have a negative charge. Sulfur is going to have a negative charge. Chloride is going to have a negative charge. Chloride is the main extracellular anion. Sodium is the main extracellular cation. And so those are important to know, is that sodium is the most prevalent positively charged molecule that is found outside of the cell, and potassium is the most prevalent positively charged molecule that is found inside the cell. So how does water bond to these electrolytes? Remember when we dump these electrolytes in water, or say we eat something salty, they dissociate. So if we had table salt, it was sodium chloride. Now when it hits our bloodstream, it's going to break apart into individual sodium molecules and individual chloride molecules. And the unique thing about water molecule is one of the few molecules that has what's called an electric dipole. So it has different charges depending on its orientation. The hydrogens have this kind of net positive charge, and the oxygens have this net negative charge. And this allows water to interact with both things that are positively charged and things that are negatively charged. So if you look at the sodium, the larger round part is an oxygen, and that oxygen has a negative charge. So in this way, oxygen from water is binding to sodium. But if you look at the chloride, the two smaller circles, which represents the hydrogens, which have positive charges, are binding to chloride. And so oxygen is unique in the fact, water is unique in the fact that it can bind to both of these types of ions. Because water can bind to both of these types of ions, water will follow these ions to do just that. And this can be described in a process called osmosis. And during osmosis, water, which in this particular picture is represented in blue, and these different ions, which are represented in red, water will move into a more concentrated ion solution in order to dilute those so that they are spread evenly throughout. So this is another diagram. On the left side, you have two solutions, and what's separating them is a semi-permeable membrane, which is a membrane that water can cross, but these different electrolytes cannot because they're too big. And so in this diagram on the left, the electrolytes, which are represented in red, are even on both sides, and so the water level is even. In step 2, we are adding some electrolytes to side B. We're dumping them in right there. And so side B is now going to be more concentrated in electrolytes than side A. And in diagram 3, you can see that in order to even this up or keep the concentrations of electrolytes the same, water has moved from part A over to part B in a process called osmosis. And in this way, water helps balance electrolytes between intracellular and extracellular membranes. In order for water to do this, it requires many different proteins, and there are transport proteins across the cell. Some ions require transport proteins, some do not. And sodium-potassium pump is an example of a protein where we do need protein to transport sodium and potassium across the cell. So without adequate protein levels, fluid balance across cells would potentially not be maintained adequately. There's another protein that doesn't play a role in transport so much, but does play a role in maintaining osmotic pressure, and this is a protein made by the liver called albumin. So this is a picture of the sodium-potassium pump, and it is a pump located on the cell, and it uses ATP, which is our form of energy, to maintain the balance of sodium and potassium within the cell. So sodium ions are pumped out of the cell and potassium ions are pumped into the cell, and the energy used for this pump is ATP. And this pump will help maintain an even set of charges between the inside of the cell and the outside of the cell, so that the number of positive charges from the potassium on the inside is the same as the number of positive charges from the sodium on the outside. The reason it's important to maintain these different charges in appropriate levels is that charges directly relate to something called pH. pH is the negative log of hydrogen ion concentration, and hydrogen happens to have a positive charge. So the charge of these different electrolytes can affect the pH of the cell. And the body will use these different electrolytes or ions to help maintain fluid balance, but also to regulate the pH. It's important to maintain body pH within a very narrow range, and for the human body, that range is 7.35 to 7.45, because outside of this range, proteins can be denatured, enzyme action can be inhibited, cells can actually experience cell death, cell membranes can collapse, and eventually you could have organ death and total organ failure. There are 3 different systems within the body that help regulate acid-base balance, and if you take metabolism class, an advanced nutrition class, or an anatomy physiology class, or possibly OChem or biochem, you may learn about some of these different systems. We have a buffering system, we have our lungs, and we have our kidneys. And our buffering system is the quickest to react. Our lungs are the second fastest to react, so we can breathe out more carbon dioxide or we can retain more carbon dioxide. And then our kidneys, although they are very efficient, they do take longer to react. So kidneys can excrete more positive charges in the urine or less, making the urine slightly more acidic or more basic, which can help neutralize the pH of the blood. Minerals. So we finished talking about water. It was rather brief, but again, in an advanced class, you can learn more. And so now we'll talk about minerals. Minerals are inorganic, meaning they are not destroyed, and some people will refer to minerals as ash. If you've ever had a bonfire and let the wood burn down 100% until there's nothing left but ash, that ash may include some of the minerals. The major minerals for humans are calcium and phosphorus, and the major minerals are classified by how much of them we have in our body. We also have many minerals that are considered trace minerals that are important but found in much smaller amounts. I mentioned that they are not easily destroyed, they're not easily changed, and they have different transport and absorption mechanisms. For example, calcium requires a specific carrier, and then it is possible to have toxicity from different minerals, as it can be difficult to excrete potentially or transport some of them. So, bioavailability. Bioavailability of minerals means the ability for our body to utilize, absorb, metabolize, distribute to the tissues different minerals we consume from food sources. And certain foods have factors that can hinder bioavailability. For example, the ability of us to absorb calcium and iron. For example, iron is found in some legumes and grains. However, because of the fiber content and something called phytates, we're not able to absorb as much of that. There is also something called oxalates that's found in rhubarb and spinach and other greens that can inhibit our absorption of certain minerals as well. So you always want to kind of investigate the food source completely before you determine that it's going to actually be a bioavailable food source for your body. This is a graph of the macrominerals and the microminerals or the trace minerals. And you can see at the top, calcium and phosphorus are minerals that are in our body in the highest percentages, where selenium is one of the lower ones. Iron, although it's so essential to our bodies, is actually found in very low amounts in our body, so it's categorized as a trace mineral. Sodium. So we just saw the role of sodium in the sodium-potassium pump, as well as an electrolyte and maintaining fluid balance. It's also important for nerve impulses, muscle contraction. However, generally speaking, we get plenty of it. So it's very, very rare for sodium deficiencies to develop in healthy people. And this is because the typical American diet is so high in sodium foods. Generally speaking, restaurant foods, sandwiches, deli meats, cheeses, condiments, canned soups are all high in sodium. Fast foods are high in sodium. And in certain people, sodium can increase blood pressure due to its relationship with fluid. However, not every single person is going to have a rise in blood pressure due to sodium. It's also possible that very high sodium diets cause increased calcium excretion. And remember, calcium is positively charged, and so potentially the body is trying to balance the charges by getting rid of something else with a positive charge. Sodium recommendations. So there are adequate intake levels set for sodium. And generally speaking, everybody is getting plenty of sodium. There is also an upper level set for sodium, and it's 2,300 milligrams. The average intake for Americans is 3,400 milligrams of sodium per day. And so we're exceeding the upper level by about 1,100 milligrams per day. Risks of this are, like I mentioned, high blood pressure, heart disease, which could lead to stroke, etc. And sodium is found in so many foods that even small amounts are sufficient to meet our adequate intake levels. Chloride. So chloride comes next because it is often consumed at the very same time that sodium is. And sodium chloride is our typical table salt, which can be added at the table or to different food sources. Chloride is also an electrolyte, so it's important to electrolyte fluid balance, that acid-base balance, and it's found as part of hydrochloric acid, which is stomach acid necessary to digest all of our food. So chloride, just like sodium, is essential. We can't live without it, but we generally tend to get plenty of it. Deficiency for chloride is pretty rare unless you're vomiting or have extensive diarrhea, at which point sodium deficiency is also possible. But if you vomit a lot, it's possible that you're vomiting up a lot of that stomach acid containing the chloride and then not eating sufficiently to replace it. Potassium. So potassium is something that, unlike sodium and chloride, we actually need more of. Remember that potassium is a positively charged intracellular cation, and so just like sodium and chloride, it helps with fluid and electrolyte balance. It's also important for the cells. It's important for nerve and muscle contractions, or nerve signaling and muscle contractions. And a lot of times when we think of our muscle, we think about our biceps or triceps or quads, etc. But potassium is key to every single muscle in your body. And one of our more important muscles in our body is our heart muscle. So when we don't have appropriate levels of potassium, either too high or too low, we can experience abnormalities with our heart contraction. And we can have rapid heartbeat, we can have slow heartbeat, we can have irregular heartbeat. And in the worst case scenarios, the heart can actually stop. And a fun or not so fun fact is in some states, and definitely in the past, they've actually used very high levels of potassium in injection forms as part of the death penalty. So, super high amounts of it could possibly be dangerous. However, in healthy people, we generally don't see any issues, especially from food sources. The only time we see possible issues are for people with kidney disease because they have trouble excreting potassium. So for healthy individuals, don't worry. You actually need more potassium. And the reason that you need more potassium is because it's the opposite of sodium. And while sodium is associated with high blood pressure and heart disease, potassium and all of these great fruits and vegetables that it's rich in are associated with lower blood pressure and lower risk of heart and cardiovascular disease. So they're actually changing the food labels to require potassium labeling so that Americans can get more potassium in their diet. So don't be afraid, it's actually really good for you. The reason that our diets are so high in sodium and so devout in potassium is because of food processing. And when we process food, we generally remove some of the whole grain and we add preservatives. And sodium is generally used as a preservative, as well as sugars and fat. So we're kind of stripping the food of its original content and changing it significantly. And this causes the American food supply to be rich in sodium, which is represented here by the kind of orangish bar, and low in potassium. One way to increase your potassium intakes is to eat whole foods, which are pictured at the top. So whole fruits, whole vegetables, whole grains. If you're going to have meat, real pieces of meat from the animal versus processed meat like salami or lunch meat. If you're going to have dairy products, real dairy products versus processed dairy products. Those are great ways to increase your potassium level. Calcium. I'm sure you guys have all heard of calcium, and we all know that it's very important for the bones. It's also important for muscle contractions, nerve function, blood clotting, and blood pressure. And it's the most abundant mineral in the body. Our bones serve as kind of a calcium bank. And so if we're not eating adequate calcium levels from food sources, what our body will do to maintain normal blood calcium concentrations is pull from the bones. And from a survival standpoint, this is beneficial because it will allow normal calcium levels in our blood, which can help with all these important processes, nerve function, blood clotting, blood pressure, and immunity, as well as muscle contraction, very vital to life, but it could actually over time deplete the bones of their mineralization or their calcium levels and lead to weakened bones. So it's very important that people consume adequate amounts of calcium so that they have circulating levels to perform these functions, as well as excess circulating levels that can be deposited and stored in the bone. Younger children have higher calcium needs than adults, and after age 71, the needs for men and women increase, and for age 50 in women, the needs do increase. Calcium balance is very closely and tightly regulated to prevent calcium toxicities or deficiencies, and so in the case of low calcium blood levels, we can pull from the bone for calcium storage. We can also change how much calcium is absorbed in the intestine, depending on our calcium storage, and we can change how much calcium is reabsorbed into the bloodstream instead of being deposited in the urine by the kidneys. So in healthy people with healthy thyroid, kidneys, intestine, they don't have to worry so much about calcium balance because we have this system of checks and balances. And there are some important hormones that play a role in calcium balance. Vitamin D, which remember is a vitamin and a hormone, parathyroid hormone, which is different than the thyroid, but similar. So it's not the actual thyroid, it's actually 4 glands that sit on top of the thyroid hormone. And calcitonin, which is a hormone that inhibits the activation of vitamin D and prevents calcium reabsorption in the kidneys. So those hormones written in blue are important for calcium balance. Maintaining blood calcium in potentially a simpler diagram: when you are eating adequate sources of calcium, like I said, there is plenty of calcium in the blood to do all of the functions of calcium, as well as to deposit it in the bone. So this is like your bank account for calcium. You're able to save your calcium, put it in the bone, and the bone is strong. When you're not consuming adequate sources of calcium from diet, there is not enough calcium circulating in the blood. However, since calcium is so crucial, what will happen is the bone will break down so that it can immediately deposit calcium in the blood, and the calcium levels in the blood can stay the same. So what you may notice in this picture is the calcium represented by red circles in the bloodstream stays the same. However, the bone is changing based on the dietary intake. So if you go and have a blood test done and they measure your calcium levels and it comes out normal, that actually isn't very representative of your bone health, because your bones will sacrifice themselves to maintain a normal blood level of calcium, since it's so crucial. So additional testing would be needed, such as DEXA scans or bone scans, to truly evaluate bone health. Phosphorus. Phosphorus and calcium are closely related because phosphorus also plays a role in mineralization of bones and teeth. Phosphorus is part of every cell. Maybe you remember phospholipids. Phosphorus is also part of DNA, and it's part of ATP, so adenosine triphosphate. So phosphorus is crucial for life, and phospholipids help transfer lipids through the lymphatic system. Phosphorus is a mineral that we generally get plenty of, and it occurs in many natural foods, as well as it's used as a food additive, which allows us to get sufficient amounts in our diet. Some people think we're actually getting excess amounts of phosphorus in our diet because of this, and there is an upper level for phosphorus. Magnesium also plays a role in bone mineralization and is crucial for enzyme action, muscle contraction, nerve impulses, and immunity, and basic metabolism. And sources of magnesium are generally healthy foods. So you can see down there wheat bran, almonds, spinach, cashews, oatmeal, peanuts, baked potato with skin, brown rice, peas. So it's whole grains, nuts, legumes, dark leafy greens, seafood, and cocoa. And unfortunately, the standard American diet or the average American diet is not rich in these things, which can lead to deficiency. And deficiency can upset bone metabolism, increase risk of osteoporosis, increase risk of inflammation, contribute to heart disease, high blood pressure, diabetes, and cancer. And severe magnesium deficiency could also cause, or could even cause, tetany, which is complete muscle contraction beyond ability to move anymore. It is possible to have magnesium toxicity, but you don't see this from food sources. You only see this from supplements, and the majority of magnesium is found within the bone. Sulfate. So sulfate is also important, but found in much smaller amounts, and we do generally get enough sulfate. Sulfate is the oxidized form of the mineral sulfur, and that occurs in different foods as well as some waters, and so our needs are easily met. It is also found in some sulfur-containing amino acids such as methionine and cysteine. All right, osteoporosis and calcium. So we have hinted a little bit to osteoporosis and calcium already as we've talked about calcium. But osteoporosis is a disease where there is hollowing, weakening of the bone. The bone has less of its collagen matrix and more air or space between its structure, and this can lead to increased fractures. It can lead to hospitalizations. It can lead to weakness, disability, loss of height, depending on where the osteoporosis occurs. So on the middle, or in the middle, there is a picture of healthy bone, and on the right, there is a picture of bone that's been affected by osteoporosis. You can see the spaces between the bony structure are much wider, and the spaces where there's air is much bigger. And osteoporosis affects 44 million people, mostly women, especially after age 50. There's a lot of hormone-related changes that can influence osteoporosis, and osteoporosis can be measured by something called a T-score and assessed by doing like a DEXA scan. Like I said, osteoporosis is more common in women due to estrogen changes. And so women after age 50, which is generally when menopause happens, have higher needs for calcium as well as vitamin D. Loss of bone due to osteoporosis is commonly seen, it can happen anywhere, but it's commonly seen in the vertebrae or the hip joint, and can lead to this curvature of the spine where actually discs have collapsed, or perhaps there's microfractures within the spine. Risk factors for osteoporosis. Some of them are modifiable and some of them are not. So non-modifiable, female gender, older age, both for men and women, smaller people or petite people, certain ethnicities, family history, personal history, and estrogen deficiency, especially early or surgically induced. Things that we can change, sedentary lifestyle. So weight-bearing exercise, meaning where you're supporting your body weight or more, actually makes strong bones and contributes to bone reformation or bone mineralization. And so that can reduce risks of osteoporosis. Adequate calcium, vitamin D, I would add to this, vitamin K2 and magnesium are also important for osteoporosis. Diets that are high in protein, sodium, and caffeine are going to cause some excess excretion of calcium, so could potentially contribute to higher risks of osteoporosis. Cigarette smoking, as it's very inflammatory, alcohol abuse, inflammation, as well as reduced nutrient absorption, low body weight, and certain medications. Those are steroid medications, glucocorticoids, as well as anticonvulsants. And there are some main stages in life that are really important for reducing osteoporosis, and the main stage is the bone development stage, which happens during childhood and adolescence, and then the second stage is the bone losing stage, which happens in midlife. Supplements. In order to meet calcium levels, many people, especially people who don't consume dairy or other sources of calcium, will choose to take a supplement. And I would recommend you always talk to your doctor before taking any supplement, as it is possible to have toxicity from many of them. There are all sorts of different sources of calcium supplements out there, as you can see and potentially have seen if you've gone shopping for them. Some calcium sources will say that they're natural, meaning they have used ground up bone or ground up shells, which are high in calcium. And while that may sound great, the bone and the shell, which is kind of the equivalent of the bone in crustaceans, is where our body deposits heavy metals. So if you were to grind up bone, it's possible that with that, you're also getting exposure to heavy metals such as lead, mercury, cadmium. And so bone or shell sources of calcium are potentially not the best ones to take. Quiz. All right. So the body generates water during, hopefully you said D, breakdown of energy nutrients. Regulation of fluid and electrolyte balance and acid-base balance depends primarily on what's the big organ? It's the kidneys. So that's the most important organ. The distinction between the major and trace minerals reflects B, the amounts of their contents in the body. The principal cation in extracellular fluid is A, sodium. The role of chloride in the stomach is to, hopefully you remember it's part of stomach acid, so maintain a strong acidity. Which would provide the most potassium? Bologna, potatoes, pickles, or whole wheat bread? It's actually potatoes. Potatoes are loaded in potassium, especially if you eat them with the skin. So eat whole potatoes with the skin, not French fries that are going to have less potassium because no skin and more salt. Calcium homeostasis depends on vitamin D, calcitonin, and parathyroid hormone. So hopefully you remember that homeostasis means balance. Calcium absorption is hindered by oxalates. These are compounds found in food that may reduce absorption of certain minerals. Specifically, calcium and iron are often the targets. Phosphorus assists in many activities in the body, but not B. Phosphorus is not involved in blood clotting. And most of the body's magnesium can be found in A, the bones. All right, thanks for listening today, and see you next time.